Alright, so in this lecture today we'll be doing revision, and we'll be starting with the first chapter, which was about finding the root and interpolation. So let's begin with the bisection method. In this method you find out the root in a way that you cut an interval into two parts. Alright, so for example, we have any function, say f of x. Okay, it should be continuous. We find 2 points, say a and b, such that a is obviously smaller than b, and also f of a dot f of b should be negative. Alright, and then we find the midpoint, say t. Now t is the root of the given function f of t equals to 0. Now we divide that interval a and b into two parts where t is the midpoint. So now if f of t into f of b is negative, then a is replaced by that new t. Or if f of t and f of a, the multiplication of those two terms, are negative, then b is replaced by t. Now we have to continue doing these steps until and unless we get f of t as 0. Now in any example, you will always be given that up to how many significant figures you have to continue. So it will depend at what point you will stop doing the iterations. Now let's take this for an example. The function is x minus e to the power minus x equals to 0. And the graph is also given, but that is just for your reference. Now how do you take this a equals to 0 and b equals to 1? This can be done by trial and error. You put the values like 0, 1, 2, 3 and so on in the function which is x minus e to the power minus x. Whenever you get a set of positive and negative answer, that is the interval that you take. Why we do that is because you can see in the graph, see, wherever the graph cuts the axis, alright, the point before that and the point after that should be either positive and negative. So whenever you achieve a combination of one positive answer and one negative answer, the root is going to lie between that only. Alright, so over here we use trial and error. So when we put a equals to 0, we got the answer to be -1. And then when we put x equals to 1, we got a positive answer. So with that combination of negative and positive, we say that the root is going to lie between this interval a equals to 0 and b equals to 1. Now we make this table and find out the root. For the first iteration, we have a equals to 0 and b equals to 1. We find the midpoint, which is c, that is a plus b divided by 2. That gives me 0.5. And then I see which is the part a or b that I'll be replacing with the c. Now when I do f of a into f of c, I'm going to get a positive answer. When I do f of b and f of c, I'm going to get a negative answer. That's why I'll be replacing a with c. Now again let's continue. Our new a is 0.5, our new b is 1. When I use the formula for c, which is getting the midpoint of these two, which is 0.5 plus 1 divided by 2, I'll be getting 0.75. Then I will find out the multiplication of f of c with f of a and f of b. With f of a and f of c, I'll be getting a negative answer. That is why I will be substituting c over here as the new b. Now again we will repeat the same step. A, b, find out the midpoint and find out the value of f of a into f of c. Continuing these iterations, we will be reaching a point where we will be getting c as 0.565, a as 0.562 and b as 0.569. So you see that the root has very less difference. and that's why our final answer becomes 0.565. So this was the bisection method. This was the bisection method where all you have to remember is how to find out C, and because it is the midpoint, the formula is easy, which is A plus B divided by 2. Now let's have a look at another method, which is the regular falsy method, also known as the false position method. Now in this, we know the formula for slope. So if I have a slope m, it is going to be f of b minus f of a upon b minus a. So from the graph over here, we can see the point x0, x2, x1, x3, x4 and so on. So by this we are trying to say that in the first iteration our slope is over here. In the second it will go closer towards the curve. In the third it will again be closer towards the curve. Hence we will be finding out slopes in a way that we move one step closer to the curve of the function. This is the basic method. Let's have a look at the theory. The convergence process in the bisection method is very slow. It depends only on the choice of the endpoints of the interval a and b. The function f of x does not have any role in finding the point C. It is used to only decide the next smaller interval a, c or c, b. A better approximation to C can be obtained by taking the straight line L joining the 2 points a, f of a and b, f of b intersecting the x-axis. To obtain the value of C, we can equate the two expressions of the slope m of the line L. So now you know that whenever you have the slope f of b minus f of a upon b minus a, it is used to find the value of C. All you need to remember in this method is this formula for C. This formula of C is to be remembered. Then again the same thing is followed, that whenever we choose an interval, it should be a combination of f of a and f of b. Either of them should be negative so that their multiplication also results into a negative term. Now let's have a look at the example over here. The function was given as e to the power x minus 3x squared gives 0. Here is a graph for reference. You see there can be 3 roots possible over here. But let us assume that a is 3 and b is 4. You could take any other combination as well. Whatever interval gives the combination of 1 f of a and f of b multiplied to be negative can be considered. Here I am taking a as 3 and b as 4. Now, when we do the iteration, we take the initial values a as 3 and b as 4. We calculate the C by using the formula that I highlighted before. This is the formula that we use to calculate the value of C. Now, the value of f of a and f of c is positive. That's why we will be replacing a as c and b is recurred again. Now this becomes our new a and new b. Using the other formula, we also obtain c. Again, multiplying f of a into f of c, we get a positive answer. So we replace a as c. We get the new a and the new b. We find out c. Again, by multiplication, we get a positive answer, and by repeating these iterations, we see that the root is 3.733. So that is our answer. Now before going to the next method, let's see if anybody has any doubt. Please write your doubts in the comments below, or if you do not understand anything. Alright, since there are no doubts, let's move forward with the Newton-Raphson method. Now, in this method, we again try to find the root by using the slope of the tangent at a given point. Let the given equation be f of x equals to 0 and the initial approximation for the root is x0. Please remember that in the previous methods, we were approximating by having an initial interval. Over here, we will have a single initial approximation, a single root that we will carry forward. Draw a tangent to the curve y is equals to f of x at the end. The tangent and extend the tangent until x-axis. Then the point of intersection of the tangent and the x-axis is the next approximation for the root f of x equals to 0. We repeat the procedure until it converges with the next point. If m is the slope of the tangent at the point x0 and b is the angle between the tangent and the x-axis, then we have the following formula for the slope. Basically, we have our initial guess, which is x0. We find the next value, say x1, and we use the function upon the differentiation of that function, representing the slope. So, if say this is the curve of the function and we draw a tangent approximating a single point, we draw another tangent at the point which is closer to the curve, and thus we find the root. Let's see an example over here. The question is e to the power minus x equals to 3 log x. Now the graph is given. Again, to approximate, we can use the interval and have the initial guess. Now just by looking at the function, you can know that from the interval, say 1 and 2 or 2 or 3, which part will be closer to getting a 0. While calculating the f of a and f of b using trial and error, you can see which part gives an answer which is nearer to 0. You take that to be your initial guess. For example, in this question, if f of 1 is something and f of 2 also gives an answer but which is nearer to 0, you take 2 as your initial guess. So over here, x0 is 2. x1 will become 2 minus f of 2 upon f dash 2. That will give me 1.02418. Now this becomes your x1. You go to find x2 as x2 equals to x1 minus f of x1 upon f dash of x1. That gives you 1.22523. This becomes your x2. Similarly, you continue until you get a very minute difference. Again, this will depend on how many significant figures you are asked to approximate up to in the question. Over here, we have taken up to 2. Final answer gives 1.24682. Now, we go towards the interpolation. The basic idea of interpolation is when we have a curve and we have certain points on that curve, we try to find the point next or the point in between. So we have this method called Newton's forward difference formula. Making use of the forward difference operator and the forward difference table, this scheme simplifies the calculation involving the polynomial approximation of functions which are at equally spaced data points. Please make sure that you remember this whenever we are given a data in which they are placed at equal space. There we use this method of Newton's forward difference formula. Here we have the expression. This formula is very important. Here, x1 minus x0 is the step length h, and r can be written as x minus x0 divided by h. The value is always between 0 and 1. Now please have a look at the forward table. Here we have taken it up to 5 values. So from the question, we will be having different values of xi and fi as x0 to x5 and f0 to f5. The first difference between f1 and f0, the second will be f2 and f1, third will be f3 and f2, the fourth f4, f3, the fifth one will be f5 to f4. Similarly, when we go towards the next difference, it will be following the same procedure, but it will follow the column just before it. So in this method, you always follow the column which is preceding to the column you are working on. So for the second difference, we use this column. So it is del f1 minus del f0, del f2 minus del f1, del f3 minus del f2, del f4 minus del f3. Again, for the third difference, we follow the preceding column. And like this, we form the table for Newton's forward difference. Let's have a look at an example. These are the values of xi and these are the values of fi. We have to find f of 0.5 and f of 1.5. f of 0.5 will be lying between 0 and 1. f of 1.5 will be lying between 1.1 and 2. So whenever you are calculating this, whenever you get the answer, you will know that the answer of f of 0.5 will not exceed 7. So here you can give a check to yourself if you are doing the question correctly or not. Similarly, for f of 1.5, it will not exceed the value 23. Now, we have made a difference table for the same. For the first difference, it is 7 minus 1 giving 6, 23 minus 7 giving 16, 55 minus 23 giving 32, 109 minus 55 giving 54. In the second difference, we use the preceding column, 16 minus 6 giving 10, 32 minus 16 giving 16, 54 minus 32 giving 22. Similarly, we have calculated all the values in the table. Now we use the forward difference formula from the table and we find out the value of f of 0.5. So at f of 0.5 we have x minus x naught upon h. Now x is obviously 0.5 and x naught is 0. That x naught is this value, or you can say the first value, which is 0, upon the difference. Now you see what is the difference between the given data. It is 1 unit. That's why we have 1 over here. It is divided by the difference. My answer is 0.5. So with R being 0.5, we put it in this formula and calculate the value of f of 0.5 being 3.125. Similarly, we can also calculate f of 1.5. Before moving further, let's see if you have any doubts. Alright, let's continue with Newton's backward difference formula. Now this is another way of approximating a function with an nth degree polynomial passing through n plus 1 equally spaced points. Please remember, even Newton's backward difference formula is used for equally spaced points. Now this is the formula for Newton's backward difference. Make sure you go through this. Here, the same operators can be used. There is a small change from the formula that we used in the Newton's forward difference method. There is a change in the sign, and also over there the R we used and over here the S we used uses the first and the last point respectively. Let's have a look at an example. The S that we calculate over here is done by using xn value. In the previous method we used x naught. We are using the same question and we are finding the value of f of 0.15. So again the difference is the same. 0.19867 minus 0.09983 will be giving me 0.09884. 0.29552 minus 0.19867 will give me 0.09685. The table is as similar as to the previous method. The only difference over here is in the formula. We put the values in the formula and get the answer. Now, before we move towards the next method, let's have a question. Please answer in the comments below. seems to be nobody responding. Alright. Let's see Newton's divided difference formula. Here there will be a change in the way you make the table. Let us assume that the function f of x is linear. Then we have f of x1, f of xi minus f of xj upon xi minus xj, where xi and xj are any two tabular points, and they both are independent of each other. The title is self-explanatory. It is divided difference. So when we have a table, let's have a look at the table. So when we have a table, x1, x2, f1 and f2, all these four values are used to find out f of xi and xj. Over here, two variables are involved, which is x1 and x2. So we are using these two values to find out this column. Similarly, in the next column, we will be using three values, which is x1, x2 and x3. In the next column, we will be using all the four values, which is from x1, x2, x3 and x4. We divide them by the first and the last point that we are considering in one particular iteration. Please have a look at the table before we move further. Now, let's see an example with the given x and f values. We can make the table like this. This 2 is obtained from 3 minus 1 divided by 1 minus 0. 23 is obtained by 49 minus 3 divided by 3 minus 1. 80 is obtained from 129 minus 49 divided by 3 minus 4. 4 minus 3. Now, this 7 over here is obtained by using the difference of 0 and 3. Similarly, after getting all the values from the table, we will be using the formula and obtaining the value of f of 0.3. Since the given data is for the polynomial f of x equals 3x cubed minus 5x squared plus 4x plus 1, the analytical value of f of 0.3 is equals to 1.831. Now there is something that you need to see over here. This method can be used for the data which are not equally spaced. You see, there is the difference of 1 unit over here, 2 units over here, 1 unit over here, 3 units over here. So for unequally spaced data, this method, which is Newton's divided difference method, can be used. Let's have a look at Lagrange's interpolation formula. Now again, this method can be used for unequally spaced data. Please have a look at the formula that we will be using. We have a question where we have to find out the value of phi at x is equals to 0 with the given set of values minus 2, 5, 1, 7, 3, 11 and 7, 34. So by using this formula, we can find out the answer, which is y will become 1087180. In all these methods, all you have to do is remember the formula. Make sure you do not make any mistakes while writing these formula, and your answer will be easy. This is the last call for any doubts if you have. We end up our today's session over here. In case you have any doubts, you can directly email or WhatsApp. Thank you and see you tomorrow.